So let's try another question that takes concepts from linear motion and helps us to understand rotational motion. A rope is wound around a wheel with a radius of 0.25 meters, and then it is pulled such that the rope and the edge of the wheel have an acceleration, a parallel acceleration, of 5 meters per second squared. How many revolutions does the wheel make after 2 seconds? Well, we know that there is an acceleration, so the angular position is theta plus the initial angular velocity omega times time, plus 1/2 the angular acceleration times the time squared. The initial position and the initial angular velocity are both 0, so that means we need to find the angular acceleration. We don't have the angular acceleration, but we have the parallel acceleration, the acceleration that the rope is being pulled at. The angular acceleration times the radius is equal to the parallel acceleration. So if we divide the parallel acceleration by the radius, we get the angular acceleration. So the acceleration of 5 meters per second squared divided by 0.25 meter radius gives us an angular acceleration of 20 radians squared. Radians per second squared, sorry. So now we want to know how many radians the wheel has turned. So we use the angular acceleration of 20 radians per second squared times 1/2 times the 2 seconds squared, and that gives us a total of 40 radians. So to convert back to revolutions, there is 2 pi radians in 1 revolution, so we multiply 40 radians by 1 revolution per 2 pi radians, and that gives us about 6.4 revolutions. So one point that was glossed over a bit in the is that the angular velocity and the angular acceleration are vectors. They have both a magnitude and a direction. The question is, what direction should the vector face? If we have a wheel that is in front of us and it is rotating counterclockwise, which direction should count? Well, the top of the wheel will be moving to the left, and the bottom of the wheel will be moving to the right. The right side of the wheel will be moving up, and the left side will be moving down. So which way do we pick? If we want to clearly define a vector with a plane, it makes a lot of sense to pick a vector that is perpendicular to the surface. So the angular velocity vector will point along the direction of the axle, so along the axis of rotation. Okay, that seems reasonable, but the axle is pointing in 2 different directions, so how do we choose? Well, to find the direction, we use something called the right-hand rule. You take your right hand and wrap your fingers around the axis of rotation so that your fingers are pointing in the direction of the rotation. Once you've done that, your thumb is pointing in the direction of the angular velocity vector. Now, if you know the angular velocity vector, then the angular acceleration vector will be in the same direction if the angular velocity is going faster, and if the angular acceleration will point in the opposite direction if the angular velocity is slowing down. It's just like position and acceleration, or velocity and acceleration. Okay, but yeah, so we want to focus on the right-hand rule for a bit here, so I'm going to switch to the document camera. Okay, so now we want to think about what is the direction of the angular velocity vector. In order to do this, we use something called the right-hand rule. So our first case, we want to look at a spinning disk, and it is rotating clockwise, as shown below here. So that means the disk is turning like this. So it is turning clockwise. And so we want to figure out what direction is the angular velocity vector. So in order to do this, we use something called the right-hand rule. So with the right-hand rule, what we do is we take our right hand. So it's pretty common on exams especially. Someone will be writing with their right hand, and then they'll try and do the right-hand rule with their left hand, and they'll get exactly the wrong answer. So you always want to use your right hand. So you take the right hand and you grab the axle. Right, so the wheel here is spinning this way, so we want to grab the axle, and we want to grab it so that our fingers are pointing in the direction that it is turning. So if we show here, the wheel is turning clockwise, and my fingers are also going clockwise. So now, that means that the direction that my thumb is pointing is the direction of the angular velocity. So notice, when I do this, my thumb is pointing into the page. So the correct answer here is into the page. So one thing to watch out for that causes some confusion is the directions. So I'll pull out my mini screwdriver to show the directions. But up, down, left, right are all vectors that are within the page. and then into the page and out of the page are perpendicular to the page. So that means if we talk about up, up is this way, so it's pointing up the page, down is pointing down the page, left is pointing to the left, and right is pointing to the right. Out of the page, so that is pointing straight out of the page like so, and so we often use out of the page as a symbol like this, so that is out of the page, and then into the page we do a X like this, so it's kind of like we're seeing the the tail of the arrow. So an X here is telling us that the vector is going into the page. So don't be confused by this. Up means up the page, downs means down the page, perpendicular to the page is into and out of the page. Okay, let's try another one. So in this case, we have a spinning disk, and it's rotating again in the clockwise direction, but this time it's kind of rotating like this. Let me hold it like so. So that means that it's within the left, right, and into the out of the page plane, and it is turning clockwise. So once again, I will take my right hand, I will grab the wheel, and when I do that, my thumb points down the page. Right? So basically, I'm got my wheel turning this way, so that means my fingers go this way. So if we were looking at this from above, then the wheel would be turning clockwise. And so that means my fingers would go clockwise, and that causes my thumb to point down the page. So in this case, the answer would be down. Okay, so this one you have a bunch of these to do. I think this is one of those concepts you just have to practice a fair number of times. So I think we've got 3 of them coded up for you, and so just get your practice. Don't be shy. Take out your hand and grab the axle. Figure out what direction the velocity vector is going. All right. So in any case, I think you should do some of these right-hand rule problems. And next we're going to discuss the moment of inertia.